In this video, we'll go over some more examples of solving standard problems using the simplex method. We'll start with the farmer problem, which I believe we used as our first example of setting up a problem so as to start on it with the simplex method. But of course, we haven't finished it yet. We haven't actually done the solution with the simplex method. We just set up the initial simplex tableau. Since we have already set up the tableau for this function, we went through the process of introducing the slack variables and so forth. So I'm going to skip through that. You can review that if necessary. The initial simplex tableau that we arrived at when we did that is the one that's shown right here. X and Y being acres of corn, acres of soybeans, U, the slack variable representing unused land, V representing unused, was V storage space? No, V was unused capital, and W was unused storage space. And P, of course, is the profit. So now that we're ready to start work, we check through this portion of the bottom row and see that the most negative number there is minus 90, which determines that our first pivot element will come from column 2. We check the ratios 1 into 320, 100 into 20,000, and 40 into 19,200. We'll pick the smallest of those ratios. The smallest one turns out to be the 100 into 20,000. So the 100 becomes our first pivot element. The first row operation we need is to turn that into a 1. So we'll multiply row 2 times 1/100th in order to accomplish that. Having done that, our new row 2 is as shown in this tableau. And to finish this step, we need to turn this 1, this 40, and this minus 90 into zeros. The row operations which would do that for us would be what? They would be row 1 minus row 2, row 3 minus 40 row 2, and row 4 plus 90 row 2. When those three row operations are performed, we arrive at the tableau shown right here. We have finished putting that column into the unit form, and so we've completed our first step. Let's give an interpretation for the tableau in terms of which corner point of the solution region this tableau represents. Notice that it's the X column and the Y columns which are not in the basic form with a 1 and the remaining number 0. So we set X and X and V. The X and V columns are the columns that are not in that form. So we set X and V equal to 0. Cover up those columns and see what equation corresponds to each of the rows. The first row would say U is 120. The second row would say Y is 200. The third row would say W is 11,200. And the bottom row would say P is 18,000. So where we are in the solution process is we're at the corner point where X is 0, Y is 200, and P is 18,000. So that corner point would correspond to a strategy of planting no corn, planting 200 acres of soybeans, and it would bring in a profit of $18,000. V is 0, which says it would use all the capital available. U is 120, which says there would be 120 acres of land that's not planted in either crop. Let's put that together with this fact. If remember, we had a 320 acre farm. If we're planting no corn and 200 acres of soybeans, then that leaves 120 acres of land not planted in either crop. And the W is the slack variable in the storage constraint, so that would say that we're going to have 11,200 bushels of leftover storage space if we follow that strategy. Move on to the next pivot element. we have now only one negative number here in the bottom row, so automatically that determines that the next pivot element will come from column 1. We have these three candidates, so we divide 1/2 into 120, 1/2 into 200, and 80 into 11,200. Find the smallest positive ratio there, and it turns out to be the 80 into 11,200. So we will want to turn 80 into a 1 and turn these other numbers in that column into zeros. Turn 80 into 1 by multiplying row 3 times 1 divided by 80. That will take you to this simplex tableau. And then the remaining row operations to be done will be row 1 minus 1/2 row 3, row 2 minus 1/2 row 3, and row 4 plus 15 row 3. Once those row operations are performed, we arrive at this tableau. We have finished work on this column. We can now see that we've finished. We can see that we've reached the optimal solution because there are no more negatives down here. So it's just a matter of interpreting where things stand. Our columns which are not in the basic form of a 1 and the remaining number 0 are the V column and the W column. So we'll start out setting those variables equal to 0 and then looking at the equations represented by the rows when we do that. The top row will give us U equals 50. The second row will give us Y equals 130. The third row gives us X equals 140. And the bottom row gives us P equals 20,100. So let's describe in words what we have learned. We've learned that the planting strategy which will produce the greatest profit is to plant 140 acres of corn, 130 acres of soybeans. The profit obtained will be $20,100. This is, I believe, the same solution that we came up with when we treated this problem geometrically. We also pick up the information about the slack variables. V was the slack variable in the capital constraint. So it says that if we follow this strategy, we'll use all our money. W was the slack variable in the storage constraint. So this equation says that if we follow this strategy, we'll use up all our storage space. U was the slack variable in the land constraint. U equals 50 says we'll end up with 50 acres of unused land. And of course you can see that also by seeing that this acreage planted adds up to 270, and we had 320 acres in the farm. So that's consistent with 50 acres of unused land. This next example we're going to look at in pretty close detail before we start. It's a new example. We haven't seen this one before. It has to do with a developer who is planning to build a subdivision, 3 kinds of houses: townhouses, single-story detached houses, and 2-story detached houses. And the bottom line is how many houses of each type should he construct in order to maximize his profit. So one thing that's fundamentally different about this problem from the other linear programming problems we have treated is that we have 3 variables: number of townhouses to be built, number of single stories, and number of 2 stories. So this is a problem that can't be done geometrically because we can't graph in 3 dimensions, not very effectively at least. But we'll see that we can solve it via the simplex method in the same way that we've been doing 2 variable problems. This problem requires a very close reading. In particular, this sentence right here tends to throw students. On 1 acre, he can put 6 townhouses or 4 single-story houses or 2 two-story houses, and he has 60 acres available. So there's a constraint on how many houses can be built based on the limited amount of land. But many students, when they try to write down that land constraint, do it wrong. So I want to put you on notice to be careful about that. There's also a capital constraint. Here we have profit information. We have the available capital. We have the available labor information and the labor requirements for building the houses. But again, except for the fact that this one constraint tends to be tricky, or I shouldn't say tricky, it requires a careful reading. And the fact that it's a three-variable problem, of course, there's nothing fundamentally different about this from other problems. We'll use x, y, and z for our variables, x being the number of townhouses, y the number of single stories, and z the number of two stories. And when you come to the constraints, this is what you will come to. The land constraint does not have coefficients 6, 4, and 2, which are the numbers in the problem, but rather the coefficients are 1/6, 1/4, and 1/2. So do a careful reading and make sure you understand why. The reason basically is that the information we have, for example, is that with the townhouses you can build 6 townhouses per acre. But what we're writing down here is the total amount of acreage used for building townhouses, acreage used for single stories, and acreage used for two stories, and that can't exceed the 60 acres available. The acreage used for townhouses, 6 houses per acre, translates into 1/6 of an acre per house. So it's 1/6 acre per house times the number of townhouses. That would be the total amount of acreage used for building townhouses. The other constraints are pretty straightforward, except for the fact that I have lopped off a bunch of zeros. This second constraint is the capital constraint, and if you just fill in the numbers as they appear in the problem, you've got 3 extra zeros, 40,000, 50,000, 60,000, and 2,880,000 are the numbers that you read straight out of the problem. But I am dividing I'm dividing through the second inequality by 1,000 to just knock off those zeros to give me something easier to work with. And in the third constraint, this coefficient starts out as 2,500, 3,000, 4,000, and 240,000, and I'm dividing by 100 to knock off some extra zeros there. So that's optional, but it makes the graphing easier to do by doing that. And in the same way, the profit is in thousands of dollars. So I'm representing my profit, instead of writing 15,000, 18,000, 20,000, I'm just writing 15x, 18x, 20, 15x, 18y, 20z, with the understanding that we're talking about profit as measured in thousands of dollars. So these are simplifications for my own convenience. So when we take these three constraints and introduce slack variables appropriately, we pick up a u, v, and w slack variable. The profit function put into standard form is shown here. So this is the input that goes into the initial simplex tableau. An x and y column and z column, these were our original variables. The three slack variables u, v, and w from each of our three constraints, our profit P, and the numbers from the right side. So let's begin the process of solving using the simplex method. The most negative number in the bottom row is the minus 20. So the three ratios we check are 1/2 into 60, 60 into 2880, and 40 into 2400. The smallest ratio turns out to be when we divide 60 into 2880. So the 60 becomes our first pivot element. We want to turn that into a 1, which is done by multiplying row 2 times 1 over 60. And then we have 3 row operations to finish up work on that column. The row operations would be row 1 minus 1/2 row 2, row 3 minus 40 row 2, and row 4 plus 20 row 2. When those 3 row operations have been performed, this is where things stand. So after the first step, this is where we are in our solution process. To start interpreting where things stand, we set x equals 0, y equals 0, v equals 0 because of the way their columns look. And we read off for the other variables, u equals 36, z is 48, w is 480, and p is 960. So if you tried to imagine the solution region as being some pyramid-like solid in three-dimensional space, this simplex tableau would represent a corner point corresponding to a strategy of making no townhouses, no single stories, putting all the effort into detached two-story houses where you could make 48 and the profit would be 960. Remember, that's thousands of dollars. When we go on to the next step, the most negative number in the bottom row is the minus 5/3, so the pivot element will come from the first column. Remember, we're looking for smallest positive ratio. Two of the numbers in the first column above the bottom row are negative. So really there's only one candidate for pivot element. It's the 2/3. You don't even have to check ratios in this case because 2/3 into 48 is the only way to even get a positive ratio. So 2/3 is automatically going to be the next pivot element. We need to multiply the second row by 3/2 in order to turn that into a 1. And then the remaining 3 row operations would be what? Row 1 plus 1/6 row 2, row 3 plus 5/3 row 2, and row 4 plus 5/3 row 2. When those row operations have been carried out, this is where things stand, and you can see that we've now reached the optimal solution. There are no longer any negative numbers in the bottom row, so we know that we're done, and it's simply a matter of interpreting our final tableau to see what the solution is. The y column, the z column, and the v column are not in the basic form, so those variables get set equal to 0. The first row tells us u is 48 when we block out the y, z, and v column. That's what the equation would be that first row represents. The second row tells us x is 72. The third row says w is 600. And the bottom row says p is 1080. So our optimal solution would be to build 72 townhouses, no single story, no two-story, for a profit of $1,080,000, which would be $1,080,000. Before leaving the problem, though, let's give a little thought to the slack variables. U was the slack variable in the land constraint. So U equals 48 says if we follow this strategy, we're going to have 48 acres of land, which is not used to build houses. That's consistent if you think about it, because building 72 townhouses, since they take only 1/6 of an acre each, means 72 townhouses would take only 12 acres of the 60 available acres, so that would leave 48 acres undeveloped, or at least not being used for houses. V being 0 says there's no unused capital. We'd be using all the available funding. W equals 600 says there would be some leftover labor. Now remember, I introduced the slack variable W after I had divided through that inequality by 100 just to simplify it for graphing purposes. So you have to be a little bit careful in interpreting what this W equals 600 means. That's not 600 hours of labor. We got W equals 600 after we had divided the equation by 100 to start with. So actually this is if you wanted to go back and translate it into hours of labor, you'd have to go back and re-multiply times that 100 to put it back in the original units, which would be 660,000, I guess. So that means of the original hours of labor available, 60,000 of those hours would not be used if we just built 72 townhouses.